Okay, so welcome back. In this video, we're going to focus on variable selection techniques. This is kind of a broad topic, so we're not going to get into everything. I just wanted to show you some examples of how we can deal with a large feature space, and then we'll also look at some pre-processing options in caret. Okay, so why do we care? So if you were just kind of thinking about this kind of logically, it seems like the more information you give an algorithm, the better job it's going to do because it just knows more about the problem and the feature space. So imagine, for example, if you're needing to buy a car, if you spend some time gathering a lot of data, so you know a lot about different cars, pros and cons, then that's just going to make you a better consumer, so you're going to be able to make a better decision, right? So the idea is that, knowledge is power. The more we know, the better the result, right? So it turns out that's actually not always the case in the world of machine learning. So this is known as the recursive dimensionality, or the Hughes phenomenon, named after this Hughes researcher. So the idea, and this was coined early, like in the 1960s, as you can see there. Okay, so look at this is a graph from this paper by Jane et al. So we're basically graphing classification error against the number of predictor variables or the number of features. The dashed line is when we have a model with 1,000 training samples versus, and then this solid line is when we have a model with only 100 training samples. So basically, when you have a large sample set, you can see that the accuracy tends to increase as you have more samples, and it eventually kind of levels off, so we're really not getting a lot of additional performance. Maybe it's because all the information has already been gathered. You're not really getting any additional information in the added variables. So that pattern kind of makes sense. In contrast, this other pattern is kind of an interesting result. So here we're seeing improved model performance up to, say, 20, 25 variables. And then instead of the model continuing to improve or kind of level off, it actually gets worse. It actually gets substantially worse towards the end here. So in this feature space where we have a smaller set of training samples, 100 as opposed to 1,000, we're actually seeing reduced model performance or more error with more predictor variables, which seems kind of counterintuitive. But the explanation for this is that when we have more predictor variables, we have a more complicated feature space, more dimensions to worry about, which means that we have a more complicated space in which to solve a problem. And that generally means that you're actually going to have more training samples in order to really kind of define or describe that space. And with the reduced set, the increased complexity is not offset by the increase in information. So that ends up resulting in decreased error, which effectively is the Hughes phenomenon, increased error rates or decreased accuracy, which effectively is the Hughes phenomenon or the recursive dimensionality. So this is generally a problem, more so when we have small training data sets in a large feature space. You may be thinking, well, what is a small training data set? Well, again, that's kind of hard to say. I mean, here that we saw a big difference between 100 samples and 1,000. But that's going to depend on the complexity of the problem, the algorithm that you're using, the features, the dependent variable you're predicting. So there's not really a hard number there. But what this does suggest to us is that we may actually get a better model if we take the time to actually pull out a optimal subset of features as opposed to throwing everything but the kitchen sink at it. Okay, so there's kind of two broad ways to do this. Feature selection is generally when we're picking from the currently available features, right? So we have features A, B, C, D, E, F, G, H, and we use some type of method to decide to only use A, D, H. So we're just grabbing a subset of the features. In contrast to that, feature reduction are generally techniques where we create new features from the original features. So from A through H, we generate new features X, Y, and Z, right? So subset of the original, new features from the original, right? So I'm just going to talk about some different methods we use to accomplish this. Okay, so within caret, there's a there's a feature selection tool built in known as RFE, or Recursive Feature Elimination. There's a couple different ways that it works, but one of the common implementations is to actually use the random forest variable importance. So the idea basically is that we run a model with all of the variables. We assess the variable importance, and then we throw out the least important variables and rerun the model. And we continue to do that, and we assess model performance using those different subsets of variables, again, throwing out the least important variables through each iteration. And then we effectively just take the set of variables that provides the best performance. So that might end up actually being the full data set. It actually might end up being a small set of variables. It just depends, right? So this is showing how you could set that up. So here I'm setting a random seed for reproducibility. I'm using this RFE control function to set it up. So this defines the random forest method. I'm doing it with tenfold cross-validation. This is the sequence to try. So we're trying 1 through 147 by 5. And what we're really optimizing here is the mtry parameter for a random forest. So here this RFE function actually does that, and then it spits back a set of optimal predictor variables. So that's effectively just based on the random forest variable importance estimates. So that's recursive feature elimination as implemented in caret. Another tool that I use sometimes to do this in R is this rf.modelSelect, which again is also based on random forest, and it was implemented here from this Murphy 2010 paper, and it's in this RF utilities package. So this is actually fairly similar to the method that's developed or included in caret, but it has another component which looks at how parsimonious the model is. So basically, the idea is that parsimony is coming up with a good answer with reduced complexity. So it takes into account not just like model performance, but also complexity. So effectively, the model is penalized for having a large feature space or a large number of variables. So the idea here is to try to balance between model performance and large feature space or number of variables. So we have this measure of parsimony, or how parsimonious or simplified the model is, or how large the feature space is. I mentioned this earlier when we were talking about variable importance with random forests, but the Baruta method, which again we're not going to talk about in detail here, this is another way that you can rank variables. This is a graph from a recent publication related to estimating burn severity from terrestrial laser scanning data. So basically we're going to take all the variables and categorize them as important, non-important, or like potentially important, and it's based on comparisons to permutated shadow variables. So that's something that's worth checking out if you want to be able to get like a list of simple decision boundaries of yes, no, maybe, as opposed to like a ranking. Okay, so again, there's multiple ways that you could do feature reduction, so creating new variables from the original set of variables. What we're going to look at here is principal component analysis, just as an example. Okay, so the idea with principal component analysis is to create a set of uncorrelated variables from an original set of correlated variables. So the idea is that variability represents information. So when we have correlation, there's effectively shared variability between variables. So if we can remove that correlation and create new variables, we can effectively capture all the information or the variability in a smaller set of uncorrelated features. So that's effectively the concept behind principal component analysis. So it's an orthogonal transformation. You're converting n correlated variables to n uncorrelated variables. Again, the idea is that variance represents information, and generally what happens is we can summarize all the variability in the original data in a smaller set of features. So maybe 10 features can be the variability or information in 10 features could be captured in just 4 features, and the added benefit that they're now no longer correlated with each other. To do principal components, you look at the correlation using a correlation matrix, and the output will be what's known as eigenvectors. And effectively, these are the values that you use to transform the raw variables into the new principal components, the uncorrelated variables. So, for example, let's see, these are the principal component layers, and then these are the original input layers. So effectively, to get the first principal component, we would take the first feature, multiply by this, take the second feature, multiply by this, so on and so forth, and then add all those together, and that would be principal component 1. And then this would be the for 2, 3, 4, so on and so forth. So we had 6 input variables, and we've transformed those into 6 uncorrelated principal components. And again, it's just the kind of a combination of the original variables. So it's the original values and these eigenvectors. Again, kind of the benefit here is that we may be able to summarize the variance, or again, the information in the data, in a subset of variables. So this is generally visualized in a scree plot. So this is the variance explained and on the y-axis, and then the x-axis is the principal component. So this is principal component 1, 2, 3, 4, so on and so forth. This is that represented as a graph. So as you can see here, the first principal component actually explains or captures 81.7% of the variance in the original variables. Then the second is 15.4%. The third is 2.5%. So out of these 6 variables, once converted into principal components, effectively 99.7% of the variance is explained in half the variables, or 3 of the variables. I mean, even 2, you've got 97.1%, which is a good bit of the variance. So we have the benefit, again, of having variables that are not correlated with each other and less variables than we had before. So that's principal component analysis. It's just one way to do feature reduction on the assumption that variability represents information. This is just some example of principal components applied to an image. So each pixel in an image. So here's our original bands as a false color composite, and here are grayscale images of the first 3 principal components calculated from the original bands. And you can see here that different principal components are capturing different information. Like here we see a very big difference between like water versus land. This is differentiating a lot like vegetation versus impervious. Here we see differentiation in the water where we have sediment versus not sediment, so on and so forth. So, different way to represent the information content in the original data. Okay, so if you're interested in applying principal components in R, there's a couple different ways to do it. There's the prcomp function in base R, so in base R installation. There's also PCA tools package, and for applying principal components to raster data, remotely sensed data, you can do that with the RS toolbox package. Okay, let's go ahead and I'm going to continue on here. So another issue other than subsetting features is that we may want to try to balance the training data set. So especially in the context of classification, but this can also be true if you talk about like range of values for regression, we want to have somewhat uniform representations of different classes or value ranges. It's generally been shown that most algorithms will tend to poorly predict a very the minority class. So, for example, there are lots of situations where, say, the true case is actually not that common. Examples would include something like feature space, like fraud detection for credit cards. What's some other options? Like maybe positive tests for like certain medical tests. So, say for example, you were trying to train a model for fraud detection, and just let's say on average, only like 0.001% of all credit card transactions are fraudulent. So if you gave the algorithm that correct proportion, then it could just say everything was not fraudulent or a legit transaction and be like over 99.9% accurate, even though that's not very useful. So that's what we're talking about here when we're talking about dealing with balanced data. So again, if the training data are not balanced, generally the algorithm, and this is true for most machine learning methods, may underpredict or poorly predict the less common class or the minority class or the one that has less samples in the training data set. So how can we potentially deal with this issue? So one option is to create data using some type of stratified random sampling. So effectively, we're like oversampling the minority class so it actually is well represented in the training set. But that's not always easy to do, especially if you don't have classification information like ahead of time that you can stratify on. There are some other techniques to potentially to do this. So one option is to randomly undersample the majority class. One issue with that is that means that you're not actually going to be using all of your available training sets, so you're going to have a smaller training set, which could result in lower accuracy. Another option is to duplicate the minority class, so just use the minority class samples multiple times to kind of balance out the proportions. And there are also techniques to synthetically generate new samples of the minority class. How this is done in caret, you can do this inside of train control, and there are a couple different options for this sampling argument. If you set sampling to down, that's going to subsample the more abundant class. If you set this to up, it's going to randomly duplicate the less abundant classes to try to balance things out a bit. And this SMOTE method is known as synthetic minority sampling technique. So it does a combination of downsampling the majority class and then synthesizing new instances of the minority class. Effectively, what it does is it takes the minority class examples, and instead of just replicating them, it replicates them with a little bit of noise, so they're a little bit different from the examples that exist. There's arguments to be made for each of these. Generally, I try up sampling, so I just simply try to duplicate examples of the minority class and see if that helps. Again, you may see improvements, you may not. It depends on the problem, the algorithm, the level of imbalance, the class signatures, the problems, the feature space. So you can't know ahead of time whether these will help. So if you're worried about class imbalance, the best thing you can do is just try. Okay, so in this last section, before we talk about tidy models, I'm going to just talk briefly about some pre-processing techniques. Okay, so in caret, there's a bunch of techniques built in to potentially pre-process data. And these are just a few options that you can specify within the pre-process argument within train. I'm going to talk about all of these, but just some common ones is you can center and scale data. You can perform PCA, or principal components, to generate new uncorrelated variables from the original data. There's options to remove highly correlated variables based on measure of correlation, Spearman or Pearson correlations. Different types of transformations like Box-Cox transformation, and like normalizing over a range. So these are some examples. How you actually apply those inside of caret is again inside of the train function when you're training the model. In this pre-processing argument, you can provide a set of tasks within combine here. So in this data, I'm centering and scaling the data. This specifically, I'm trying to train a KNN, and remember, KNN is sensitive to data imbalance. So you're going to want to center and scale the data so you don't have that issue. Again, KNN and SVM are sensitive to this issue. The tree-based methods generally aren't, so centering and scaling might not be important there. Generally, if I'm going to compare a bunch of algorithms like SVM and random forest or KNN and random forest or whatever, I'll just center and scale for all of them just for consistency. So this is just one example applying two pre-processing transformations. But if we go back to this slide, there are other options. Okay, so that's that. We have one section left, and this is just going to be an introduction to using the tidy models as an alternative to caret.